Hello friends, welcome to the tutorial session of the 8th week of this course. This is the last tutorial session and my last video lecture in this season. Today we are going to talk about different clustering algorithms. So in this week, ma'am taught you about three different clustering algorithms: the Kmeans algorithm, the hierarchical agglomerative clustering, and Gaussian mixture models. So three different clustering algorithms. I'm going to summarize the theory in a nutshell and then show you how to solve problems. Let's first look at K-means clustering, and before going into clustering, let me talk about an important important family of distances, which is called the Minkowski Minkowski family of distances. So a distance function is a function which gives the distance between two points in a particular space. All right. Now these distance functions should be able to, they need not necessarily always be the Euclidean distance between 2 points. All right. So they can be some statistical distance function as well, which tries to measure the amount of similarity in meaning between 2 points. So there are a lot of different possibilities of distance functions, and the Minkowski family of distances is one of the most basic and the most widely used distance functions in literature. So the Minkowski distance between 2 points, say we have 2 points, given 2 points x, which we write as x1, x2 till xn, say. So these are points from r to the power n, say. All right. So y1, y2 till yn. All right. So these are, say these are 2 points, and both x and y, they belong to r to the power n, the n dimensional real space. Okay. The Minkowski distance between points, Minkowski distance between x and y is given by this thing, summation I equal to 1 through n xi minus yi whole raised to the power p, and everything raised to the power 1 by p. Okay. So you are taking the individual dimensions, the individual components of the two different points, and you are taking pairwise differences, and then you are like raising them to the power of p, and then accumulating all of those terms, and then taking 1 raised to 1 by p to the power 1 by p. Okay. So when p is equal to, what you have, p is equal to 1, then what you have is called Manhattan distance, which is also called city blocks distance. When p is equal to 2, then you have Euclidean distance. Second. Yes. Yes. So this is quite straightforward, right? So this is the, for p equal to 2, this is what you would be doing most of the time. So this is the distance between 2 points in the Euclidean space, the normal coordinate geometry distance. And for p less than 1, it does not, the quantity is no longer a distance metric. Okay. So the value of p should be greater than 1, greater than or equal to 1. For lesser than 1, the triangle inequality ceases to hold. Okay. So this particular metric, the Minkowski family distance, this particular term, it ceases to satisfy the triangle inequality, and hence it is no longer a distance function. Okay. So and this is quite one of the most common distance metrics, right? And let's now go into the clustering algorithms one by one. So let's take up K-means clustering first. The K-means clustering algorithm is pretty simple, right? So let's see. Let me first write down the steps. So there you have two main steps. Okay, step 1. The step 1 is you initialize. So this is step 0, initialization. Okay, or let me write initialization. And just to remind you that these clustering algorithms, all of these clustering algorithms are unsupervised learning algorithms. Right. So you don't need labels here, you don't have labels here. Okay, all you have is a collection of points. So you have a vector space in which you have points which are distributed this way, all right, and you have to identify clusters. So these will fall in one cluster, this will fall in one cluster, right. So what happens during initialization is choose K centroids randomly. So the centroid of a cluster is the central point of the cluster. Okay, so if you take the points which belong to the cluster and you find the centroid of those points, then that's what we mean by the centroid of the cluster, right. So you first choose K random centroids, okay, and say K equal to 2, okay, and we choose these two points, say this one and that one, okay. So first we randomly choose K centroids, right. The next, this is the initialization. Now the next two steps are, so I would say step let me say step 1, okay. So what we do is assign each point a cluster corresponding to the nearest centroid, all right. So what we do is, for every point in the space, okay, we find which particular centroid is the nearest, this one or that one, okay. So for that point, for any point, okay, for this point also we are going to check whether this is closure or that is closure, right. And you assign each point a cluster corresponding to the nearest centroid. This means that say this is centroid number 1, this is centroid number 2. So this particular point is assigned centroid number 1, and this particular point is assigned centroid number 2, because centroid number 2 is closure, right. And this way you assign the centroids to every point in the, assign the nearest centroid to every point in the data set, and thus at the end of this step you have clusters, because like all of these points will likely be connected to the will likely be assigned centroid 1, and all of these points will be assigned centroid 2. So they kind of like form two different clusters, okay. So you assign the centroids, and the next step is update the centroids of each cluster, okay. So now now that you have found that all of these points, they are in one cluster, these points are in another cluster, now what you are going to do is you are going to update the centroid of the cluster. So on the previous step the centroid was this point, right. So you want to update it to the real centroid of the points that have been assigned to the particular cluster, all right. So you find the you take all the points in this particular which have been assigned centroid 1, cluster 1, and you calculate their centroid, and you update the centroid to the new location, okay. So this goes here and this goes somewhere here, okay, the centroid of the points. Okay. So, this is how the Kmeans algorithm works, and so and then you go back again to step 1, right. So, after you have updated your centroids, you go back and reassign the do the assignment of centroids again once over again, right, and you keep repeating these 2 steps, and finally when you have achieved convergence, then the centroid positions, they cease to change, right, and then you say you have achieved convergence. Nice. So, let us see what kind of problem can come in the exam. So, say we have been given 8 points. So, the points are P1 0.1, 0.6, P2 0.15, 0.71, P3 0.08, 0.9, P4 0.16, 0.85, P5 0.2, 0.3, P6 0.25, 0.5, P7 0.24, 0.1, and P8 0.3, 0.2. Now, assume we are performing K-means clustering of these points with initial means M1 equal to P1 and M2 equal to P2, P8, sorry. So, I just said that we choose the initial centroids, the initial means, right. I should say centroid. So, the initial centroids are chosen randomly. So, we randomly choose P1 and P8 as the initial centroids, say. Now, answer the following questions. Number 1, which cluster does P6 belong to? Okay. If cluster corresponding to M1 is C1 and that corresponding to M2 is C2, and number 2 is what is the population of the cluster around M2, okay, that is C2, right. So, what is the population of the cluster C2? So, what we are doing is just also another question is left. The third question is, what is the updated value of M1, and yet another fourth question is, what is the updated value of M2. Okay, let's solve this problem. So the first two questions are about what the initial cluster should be. All right. So what do? We have been given that. Let me show a part of the problem. Let's solve the first question first. Okay, let me solve this in blue. So they have asked, the question asks which cluster does P6 belong to. Okay, so we have to first find out that, like, initially before with the initial assignment of centroids, with the initial centroid values of P1 and P8, which of the centroids is closer to P6. So the P6 will be assigned the particular cluster which is nearer to it, right. So let's calculate the distances, and let's create a table for that. So the table will be M1, M2 and clusters number. Okay. P1, P2, P3, P4, P5, P6, P7, P8. Okay. Let's calculate the distance of each point from each of the two centroids, initial centroids, which are M1 and M2. Okay. So I have pre-computed the values. Okay. So what I am going to write down over here is, so how do you calculate the distance between the 2 points? I am just using the Euclidean distance. Okay. The distance between, say, P6 and P1 will be calculated as square root, or I will just take, there is no need of taking square root if you are comparing the squared values directly. So you can just take 0.25 minus 0.1 squared plus 0.5 minus 0.6 squared, this quantity, right, and then the square root of it is the exact Euclidean distance, but you can work without the square root. Okay, you don't need to take the square root if you want to just compare. So this is the distance between P6 and P1, which is equal to M1. All right. So what did I do? I just did this one, 2.25 minus 0.1, 0.5 minus 0.6, right, and this thing comes out to be equal to 0.0325, and similarly the distance between P6 and P8, which is actually M2, is equal to P6 and P8, right, which is equal to nothing but 0.25 minus 0.3 squared plus 0.5 minus 0.2 squared, which is equal to, I have pre-computed again. So P6 to this is 0.0925. Okay, and similarly, so you can calculate these two, and so we see that the distance from P6 to P1 is lesser than the distance from P6 to P8, that is M2. So the distance from P6 to M1, which is equal to 0.0325, is lesser than 0.0925, which is equal to the distance from P6 to M2. Okay, and therefore M1 is closer to P6 than M2. Okay, and therefore P6 will be assigned to cluster 1. Okay. So these distances which we calculated over here are 0.0325 and 0.0925. Okay, and so P6 will be assigned cluster 1. So similarly, if you calculate the other values, you will get this table, and this will be 0, this will be 0.2, the cluster number will be 1, 0.0146, 0.2826, cluster number 1, 0.0904, 0.5384, cluster number 1. Then this will be 0.0661, 0.4421, this is also cluster number 1, 0.1, 0.02, so this will be cluster number 2 actually. Now this one will be 0.2696, 0.0136, this will be cluster number 2, 0.20, cluster number 2. All right. So we calculated everything this way. So the answer to the first question here is C1, okay, which cluster it belongs to. Now the second question is, what is the population of the cluster around M2, that is C2, okay. So we see that how many points belong to C2, 1, 2, 3, okay. So the population is going to be 3, okay. Then the next question is, what is the updated value of M1? The updated value of M1 will be equal to, so it will be updated to the centroid of all of these points, all right, to the points of the, so it is equal to the centroid of the points P1, all the points that belong to C cluster 1, P2, P3, P4 and P6, okay, and which is equal to nothing but, so let us calculate it. How many points do we have? 1, 2, 3, 4, 5 by 5, and let us sum the x coordinates first. 0.1, 0.15, let me pull it down a little bit, yes. Then P3 is 0.08, P4 is 0.16 and P6 is 0.25, okay, divided by 5, right. So, and this comma, so the x coordinate is this and the y coordinate is again like 5, and then P1's y coordinate is 0.6, P2's is 0.71, P3's is 0.9, P4's is 0.85 and P6 is 0.5, right. And if you do this calculation, let's do it. It's 0.1 plus 0.15 plus 0.08 plus 0.16 plus 0.25, everything divided by 5, so 0.148, and this one is 0.6 plus 0.71 plus 0.9 plus 0.85 plus 0.5 divided by 5, which is 0.712, right. So this is going to be the updated value of M1. Similarly, the updated value of M2 is the centroid of all the points that belongs to M2, P5, P7 and P8, which is equal to, I have pre-computed it, it's equal to 0.247, 0.2, okay. So the answer to this question, updated value of M1 is 0.148, comma 0.712, and updated value of M2 is 0.247, comma 0.2, okay. So you will face this kind of questions in the exam, pretty straightforward, right. Let us go to hierarchical clustering methods now. Agglomerative hierarchical clustering. The agglomerative hierarchical clustering method, what it does is, it the approach is that you start with, say we have 4 points. Okay. So, what you do is initially you think that each point is a cluster in itself, okay, and then you keep clubbing together, or yeah, points which are the closest from each other, say C and D are the closest from each other. Okay. So, you first club them together, and next you see which two clusters are the closest to each other. Okay. So, you merge A and B, and then then finally you merge these two clusters. Okay. And what you end up having is called a dendrogram. Okay. So, this dendrogram can now be cut at a particular height to have certain kind of clusters. All right. Now, in the context of agglomerative hierarchical clustering, there are actually 3 kind of linkages, 3 kinds of linkages which are very popularly used. There are more in fact, but let us consider just these of them, just 3 of them. So, the first is called simple linkage, then something called complete linkage, and average linkage. There are some more as well. So, yeah. So, these algorithms are actually in the context of what kind of distance you want to, how you want to calculate the distance between 2 clusters. Okay. So, the entire idea is this way, that you have initially you have like a lot of points, right, and first you make, say, this cluster and this one is a cluster. All right. Now, how do you calculate the distance between these 2 clusters? Okay. So, the distance between the 2 clusters will be a function of the pairwise distances. Okay. So, let us say I j, say the clusters are C1 and C2, where I is coming from C1 and j is coming from C2. All right. So, you want to calculate the distance between the 2 clusters as a function of the pointwise distances, the pairwise distances among the points in the cluster. Okay. And the simple linkage algorithm, this calculates the distance between the clusters. So, distance between C1 and C2 according to simple linkage will be equal to minimum of the dij's. All right. So, you calculate the pointwise distances, and the minimum distance between 2 points, one belonging to C1 and the other belonging to C2, that is these 2 points, right, these are the closest points, right. So, this distance will be considered as let me write it as d minimum. Okay. The minimum distance between these 2 clusters, between points of this of these 2 clusters, is to be considered as a distance between the 2 clusters. All right. Then in complete linkage algorithm, this distance is calculated as the max of the dij's. All right. So, in this case, the farthest 2 points, so this point and that point, okay, the distance between these 2 points, d max, will be used as the distance between the 2 clusters. All right. And in average linkage, distance between the 2 clusters C1 and C2 will be the average of the dij's. All right. Now, tell me, now let me tell you some intuitive properties of these 3 algorithms. So, what if simple linkage does is, it tends to form clusters which are chain like. Okay. So, there is a particular very bad kind of a phenomenon which is called the chaining phenomenon. Okay. So, the idea is to club together or fuse clusters that are close by, okay, and now how do you calculate the two close, the closest clusters? Which clusters are the closest? You use one of these linkage formulas. All right. So the simple linkage would say that two clusters are very close together if the minimum distance between the points of those two clusters is very small. Okay, is the minimum. All right. So it might be the case that two clusters, maybe they are this way. All right. So most of the points, they are away from each other. Okay, but the closest distance is very small. Okay, though remaining points might be very sparse or like really far away from each other. Okay, so in that case also it will consider these two clusters to be very similar to each other, and it will fuse both of them. Okay, so this actually results in the chaining phenomenon. So let me write it down in the language of Wikipedia. So the clusters formed via single linkage clustering may be forced together due to single elements being close to each other, even though many of the elements in each cluster may be very distant from each other. Okay. So just what I just said, right? What happens in complete linkage is that the two clusters will be considered as similar or close together only if the maximum distance among the points in those two clusters is small, right? So it tends to create very compact clusters, unlike single linkage. All right. So this is sometimes desirable, and in average linkage, what happens is like it also performs kind of midway between these two, but there is a very famous problem which is called the rich gets richer. Okay, so I showed this problem in the Python programming session, in which you would see that just there are like big clusters. Okay, the bigger clusters are really big, whereas there will be some cluster which is just consisting of one single element. All right. So the rich gets richer, the poor gets poorer. Okay, so this kind of a phenomenon happens. Now this complete linkage, or the complete linkage algorithm, it tries to ameliorate this rich gets richer problem as well. So these are the different methodologies of calculating the distances between clusters, and you will be getting questions from these. Right. And also another thing that it has been observed that the complete linkage algorithm, it tends to create clusters that are approximately equal diameters. Okay, so same size clusters, right? Let me show you. Let me talk about Gaussian mixture modulus quickly. Okay, or let me quickly show you a problem. Let me quickly show you a agglomerative clustering problem which you can face in the exam. Let me write in black. So question 2, say we have 4 points, all right, A, B, C and D, and this matrix which I am writing right now, it describes the distance among these points. Say these are 4 cities, and the distances between the cities will be written down here. So 0, 10, 12, 20, again 10, 0, 5, 3, 12, 5, 0, 4, 20, 3, 4, 0. Okay. Let me draw some lines to avoid confusion. So we have to use minimum linkage. So it's it is called single linkage, and do agglomerative hierarchical clustering of these points. So, the first step that we are going to find out is find the two closest points. Okay. Find the points which are closest to each other, right. So, the smallest number among these distances is 3. Okay. So, this is the distance between like B and D, okay, B and D. So, the first points that are going to be merged are B and D. Let me write. So, B and D are here, I just merge them, all right. So, now my updated clusters are A, C, B and D have been clubbed together, then again you have A, C, then B slash D. Let me make the distances this matrix. Okay. Now, the distance from A to A will be 0, C to C will be 0, intercluster distance will be 0. Okay. So, the distance from A to C is the same as before, same will be here. A to B or D. Okay. So, what is the distance between A to the cluster BD? So, this will be the, as we are going by single linkage, it will be the minimum of the distances from A to B or D. Okay. So, the distance from A to B is 10, A to D is 20. So, the distance to A from A to the cluster will be 10, the minimum among them, all right. Same comes here. Distance from C to B or D, okay, is again the minimum of the two. So, the distance from C to B is 5, C to D is 4. So, the distance from to the cluster is going to be 4. We are putting it here. Now, in this matrix, let us find out the two closest clusters, which is 4, right. This is the minimum number here, which is the distance from C to B or D. So, the next element, that is next two clusters that are going to be fused are C and this one B or D, all right. And the only remaining element is A. So, clearly in the next step A will be merged. So, this is the dendrogram that you are going to get, all right. So, this is the answer. You will be facing this kind of questions in the exam. Let me quickly tell you about Gaussian mixture models. Pretty straightforward, madam has already taught it in great detail. So, Gaussian mixture model is nothing but a way of approximating probability density functions. Say, I will give you a quick intuition. Say, we have a probability density function which looks something this way, all right. So, say we have to make approximate this. We can say that see, this part is one Gaussian, okay. This part is another, here are 1 or 2, and there are some more, right. So, a Gaussian mixture model does exactly this, okay. So, it takes a number of individual Gaussians, okay, n of them, and then it does a linear combination of them to model the target distribution. So, a GMM is written as probability of, so the distribution can be written as summation over Ci, I equal to 1 through n times normal distribution of mu I sigma I, all right, such that summation I equal to 1 through n Ci is equal to 1. Okay. So, this is the model. This is the model of probability, and you are going to fit this to the target distribution. Okay. And for fitting it to the target distribution, you have to find the values for these parameters Ci, mu I and sigma I, right, all n of them. And how do you find these parameters? You use something which is called, you find the parameters through maximum likelihood estimation. You could do MAP as well, maximum a posteriori probability estimation as well, but commonly we use maximum likelihood estimation, okay, in which you try to find out which particular, so you find out argmax Ci, mu I, sigma I equal to 1 through n, So, you find these value with these parameters, okay, that particular combination of parameters which maximizes the probability of data given the parameters. Okay. So, this is the maximum likelihood estimation, and this particular maximum likelihood estimation problem can be solved efficiently, approximated. So, this can be calculated. So, exact calculation of this maximum likelihood estimate is sometimes intractable and at most times really computationally heavy. Okay. So, it can be approximated nicely by an algorithm which is called the expectation maximization algorithm. It is also called EM algorithm, very famous in ML literature. Okay. So, we use the EM algorithm to find the approximation of parameters. All right. So, this ends today's lecture. Thank you so much. I would like to thank you all to be a part of my first ever video lecture series, and I would like to thank NPTEL and IIT KGP and also Professor Sudeshna Sarkar for giving me this wonderful opportunity. Thank you, and see you in the next video lecture series that I am going to participate in. Bye bye. Have a nice day, night, anything.